Hello. Today we're going to talk about a topic that we wouldn't have talked about if we were taking this class 25 years ago. And that is something called extrasolar planets. Now, extrasolar planets are planets that are orbiting other stars, also known as exoplanets. So exoplanets are not planets in the solar system. So those not the 8 of our major planets, but planets going around other stars. And up to 25 years ago or so, we had no idea that stars had planets going around them. We thought they did, but you can't see planets going around other stars. So there's no way for us to know for sure if planets were going around other stars. Well, about, again, 25 years ago, there was a astronomer, who actually I took a class from at San Francisco State, who found a way to determine that planets were going around other stars. And this guy became famous overnight. Now, I don't really want to talk about this guy too much. This guy, turns out I used to be kind of like my idol. I taken this class from him. I actually got the second highest grade in his astrophysics class, the guy who discovered that planets were going around other stars. And, I got the second highest grade in his class, but there are only 3 of us in the class, so I might as well tell you the truth there. And, but now, how would you do this? How would you discover that planets are going around other stars? Well, here's how you do it. You need to look at a star and actually analyze the light from a star, get the spectrum of a star, remember the dark line spectrum, and if there's a planet going around a star, the star's not going to just sit there. If a planet is going around a star, the star is going to wobble a little bit. It's going to like pivot about a point that's the center of mass, or called the barycenter. Think of it this way: if 2 stars were the same mass going around each other, they would be the center of mass would be like right in the middle, kind of like a seesaw. If 2 people are on a seesaw and they're the same weight or the same mass, the center of mass is right between them. But if one person is more massive, then that person is going to be moving less, and the other person is going to be moving more. It's going to mean that the balance is going to be closer to the person with the more mass. Well, here is the idea. What's going to happen is that a star will wobble back and forth. There'll be a period of time where it's moving a little bit towards you and a little bit away as a planet is orbiting it. So there'll be a Doppler shift that can be noticed in the spectrum of the star. The dark lines will be either shifted towards the blue or the red, and this will be periodic. So you can infer that a planet is going around a star by seeing the star kind of move back and forth a little bit and looking at the Doppler effect, the Doppler shift. Now, sorry, all I found was this old PDF in my PowerPoint. I don't have my newer one here, but it's close to the same. Some data is off a little bit. Now, on Mauna Kea in Hawaii, there's a great observatory facility where there are a bunch of telescopes that are a lot of times being used to, among other things, see if planets are going around other stars, see if there are these extrasolar planets. Now, Justin Stevick, I might as well mention him. I teach with him. He was an assistant of mine. I teach with him now, but after he was an assistant of mine years and years ago, over like 20 years ago, he got to work at this observatory in Hawaii. And the observatory, these are giant scopes. The one they let him observe in and do research in. Let me show you. See that little thing? See that one over there? That's the one they allowed Justin to use. They would not let Justin use any of these other ones. They let him use this one. Now, it looks puny here, but really there's like I think it's a 40-inch diameter telescope in there. So it's a great scope, but compared to these, it's nothing. But Justin got to use that, and it's kind of interesting. The astronomers up here are really just the grad students. The real astronomers, the grad students are working their way to become astronomers. The real astronomers are down the mountain where it's warmer, and up at the top here, it's like 13,000 feet, freezing all the time. So the grad students are sent to do their work, kind of like Justin had to do. And then there's a feed of the information that goes down to the astronomers who are in their nice warm quarters, and they get the data that the grad students worked hard and out in the cold all night getting. So I guess it's good to be an astronomer in this case, and it's not that good to be a grad student. All right, now, well, there's the Keck telescope. They're one of the telescopes in Hawaii, giant telescopes. This data, it's all right. You don't have to know these numbers anyway. Well, the wobble of the star will determine, like, if there's a planet there. The bigger the wobble of the star means the more massive the planet. And if it's a very great wobble of a star or moving of a star, it probably means there could be another like star there, something like a white dwarf or a black hole, and we'll talk about those later. But as of a few years ago, by the star wobbling back and forth, and I'll show you a video of this to kind of like help you out. So right after this lecture, I'm going to post a little bit of a video so you can see how this is done. And this is how a star would wobble a little bit, because I'm not really showing you here, just showing you this PowerPoint. And so as of 2017, more than 700. As of now, more than 1,000 planets have been found this way. But most of these planets that we've detected have been the mass of Jupiter. And Jupiter is over 300 times the Earth's mass. Why would we be detecting only these planets, more easily detecting these planets, if they're the more massive? What do you think? Well, the more massive planets will cause the star to wobble more, and you can see a Doppler shift more easily. The lower mass planets, it would be very hard to see a slight shift in a dark line if it's a very, very low mass planet, that's what it's going to cause, but a more massive planet would cause a bigger shift. So most of the planets we were discovering at first were like this. I mean, this is a picture of Jupiter. We don't have a really good picture of any of those planets we were discovering. We infer they're there based on the wobble of the star. But this is a real picture of Jupiter in the solar system. So we think this is a gas giant, 318 times the mass of the Earth. So most of those planets were like that. Now, just take a look here. Again, you don't have to write anything down here. Nothing that we've written here do you have to write down, except to know that we use the Doppler effect, the wobble of a star, to detect that planets are there. That's one technique. I'd like you to know the technique we're using to detect planets is more important than like all the planets we're detecting, even though I'm going to talk about some that are pretty amazing. Now, look at this. Here's our system up here. The Sun, here's Mercury, here's Venus, here's Earth at 1 AU. So our system is like this, and we always thought if we find another system out there, another star system with planets, you're going to have the smaller, rocky planets close and the gaseous planets far. But some of the first systems we were finding, the Jupiter mass planets, and this means 0.44 times the mass of Jupiter, it was close. It was closer than Mercury is to the Sun. And these these yellow things represent the star. This is a star called 47 Ursa Majoris. Here's our star, the Sun, 51 Pegasi. And look, a lot of these massive planets are very close to their stars. We think, wow, that's weird. In our system, it's not like that. Well, now we're starting to think that our system might have started off a little differently. We think that Jupiter and maybe Saturn and some of the more massive planets maybe started off closer to the Sun and kind of wandered out. So it's getting us to think a little differently about how our system, the solar system, was a long time ago. So this shows you where these 6.84 times the mass of Jupiter, 10 times the mass of Jupiter, very massive planets going around these stars. If a planet gets massive enough, it's not even necessarily going to call it a planet anymore. It's going to be called a brown dwarf. And if it's more massive than that, it'd be a star. So brown dwarfs are, if something is maybe, actually some of these are very, very close to brown dwarf, like a 10 times the mass of Jupiter. Now, oh, look at this. Don't write this, too much stuff here. But there is a confirmed planet around Proxima Centauri in the Alpha Centauri system, the star that's the red dwarf that gets a little closer to the solar system. There's a planet there. And they think that this planet going around Proxima Centauri is so close to its star, that the temperature on the planet is about 2,600 degrees Fahrenheit. That means it must be pretty much a molten planet. No atmosphere, no water, but if there's any liquid, it's probably part of the planet. It's a molten planet. So we're finding planets out there that are so close to their stars that even though we don't see the planet, we can figure out they're molten planets. Very strange. Now, Here's a artist's conception. Again, we do not have good pictures of planets going around other stars. They're just too far away. And so here's a artist's conception of the way this planet might look like going around Proxima Centauri, but I think, yeah, if it's that close, it's going to be more molten. It looks like they're almost like craters and details here. I don't know about that. So maybe this artist kind of didn't, it's a good picture or a good drawing. I would think that, yeah, this impression is not necessarily the best impression, I would think, if the planet is that close to the star. Now, look at this. Here's a system in Cancer, the Crab, 55 Cancri. There is a star there, and what's orbiting it is 5 planets based on the wobble of the star, 55 Cancri, which is a star in Cancer. There's perturbations in this wobble. You can figure out if there's more than one planet there. So look at this. Here's our system. It represents our system. This is the 5-planet system. So we're finding multiple planets going around other stars. Now, I don't even want you to look at this. This is a big mess. Let me just kind of paraphrase here. There is a star that's about 127 light years away, and you don't have to write any of this down, in constellation of Hydrus. And just look at the star type. It's a G1. Do you know a star that's very close to that spectral type? G2, Sun. So this is a Sun-like star. And it has planets there that are maybe we detected by the wobble, about 1.4 times the size of Earth, but too close. It's going to be it's closer than Mercury is to the Sun, so it's going to be incredibly hot. Probably another molten planet. So it's called a super Earth if it's a little bigger than Earth, if we're discovering a planet. And we're able to get the masses of these planets just by the wobble, by figuring out the characteristics of the wobble of the star. We're actually able to figure out the masses of these planets. Here's one that's called a hot Neptune, which means about the size of Neptune, which is about 4 times the size of the Earth, close to its star, so it can be very hot. Look at super Earth at 0.09 AU, about 0.1 AU. So there's at least 7 confirmed planets and 2 unconfirmed there that might be planets. And so look at these. So with these planets, we don't think any of these planets could support liquid water, but some of them might have satellites that could. So it's not just planets that may have a chance for having water on it and maybe even life, but satellites could too. Even in our system, we think in the solar system, we have a satellite orbiting Jupiter called Europa, and we think there's a chance there's life underneath this water, this waterized surface. So even in our system, there could be places where there's life besides the Earth in the solar system. Now look at this. Here is a star called Fomolo. Here's artificial light. That's not the way it looks. Kind of looks like a big eyeball. Well, you see in this box right there, from 2004 to 2006, there's something that moved. You can't even see in here, but if you zoom in, you can, from there to there. Here is a direct image of a planet going around the star. Now, these are not good images. You say, wow, look at it, it's kind of square. No, you're seeing it's pixels. So we cannot really image planets yet. As far as seeing the planets, we can detect they're there, but we cannot see them. This James Webb Space Telescope that's supposed to go up maybe within the next year might be able to see these planets going around other stars. So we are pretty excited about the Space Telescope. Now here's another way we're detecting planets. So again, from all this last, 10 minutes or so talking about these extrasolar planets, what I really want you to know, the way we're detecting these is using the Doppler effect. If a star is wobbling, kind of moving towards us in a way, we'd have a red shift, a blue shift, a red shift, a blue shift, and we can, there's a planet, a lower mass object that we think is there. Well, another way we're detecting planets is something called a transit. Now, I would like you to know what a transit means. A transit is when a smaller body moves in front of a larger body. It's called a transit. So it's when a smaller body moves in front of a larger body. Kind of like an eclipse is when 2 bodies about the same size block each other. That's called an eclipse. It's called an occultation when a smaller body moves behind a larger body, or a larger body is in front of a smaller body. That's called an occultation. You don't have to write that down. So write down just this. A transit is when a smaller body moves in front of a larger body. Now let's say there's a star out there, and we can barely see just a pinpoint of light. And the alignment of the system, the planetary system, there are planets that go around it, is just right And about 1 out of 50 systems out there with planets are just right, where the alignment, where a planet, from our point of view, can move in front of its star. Now, if you can't see the planet because you can barely see the star, what would happen when a planet moved in front of its star? What would happen to the light output of the star? Wouldn't it dim a little bit? Wouldn't the planet block a little bit of light from the star? Maybe 1/10,000th the amount of light, depending on the size of the planet. The more light it'll block out. If it's a bigger planet, it'll block out more light. Well, we are detecting planets out there by them transiting their star. And here's kind of like a representation. Again, these are not pictures. This is what, if you were closer up and there were like a sun-like star, let's say, and a planet moved in front, you see how the planet might block a little bit of light, and then when the planet moves away, the star would be back to its same amount of light? Well, here's something called a light curve. And we didn't get a chance to talk about this too much, or maybe, I don't remember we talked about it at all when we were talking about variable stars. What happens is this: if a planet is going to move in front of its star, imagine a planet moving in front of a star, and we're measuring the light output over time. When a planet, and this represents a certain amount of light from the star, when a planet is in front of the star star dims a little bit. So there's a characteristic dip in the light of the star, not very much. We've really magnified this quite a bit here. And then when the planet moves away from the star, that represents the planet, there's the star, what happens is the starlight is back to its normal. And what we see, what we can tell is this. Look at this. If sometimes we'll see a dip, and then by looking at a star, and then maybe a certain amount of time later, we'll see that same exact dip again. Well, doesn't it make sense that if a planet's going around the star, imagine this planet around the star, so what happens is it goes behind. We don't know if it's going behind the star. And then what it does is it comes in front again with a certain period. Well, that's the period of revolution, the period of time it takes the planet to go around the star. And we are able to detect how long it's taking planets to go around their stars. And this is interesting, because if we had a sun-like star out there that we could barely see, and we get a dip right over here, and then we get another dip about 1 year later, you know what that implies? It implies that this planet goes around in 1 year. And if it's a sun-like star, about the mass of the sun, that means its distance from the sun would be 1 AU. This is another way that Kepler's third law is used, where p squared equals a cubed. I briefly mentioned it. I didn't get a chance to write it out, where the time it takes to go around is related to the distance. So the time it takes a planet to go around a star is related to how far away it is from the star. If it's farther from the star, it takes longer to go around. If it's closer, it takes less time. So we're able to figure out if there are planets out there. And sometimes if they're the size of the Earth, by how much dip it is, we can determine by if there's a bigger planet, this dip goes down farther. We can determine if there are planets about the size of the Earth, and we can determine if there are planets going around their stars in about a year and about 1 AU away. Well, that means a planet out there might be like Earth. There's a chance. So there could be liquid water on it. There could be life. So we are very interested in this. How many planets out there are similar to Earth? A lot of times we also could get multiple planets. If we get a dip like this, and then maybe sometime later a dip like this, sometimes we'll get even a bigger dip. Maybe it's separated by, could be years. It could be a bigger planet. So we could get multiple dips in the light curve. And that's inferring there are multiple planets there. But if you only get one dip, it's not confirmed. There could be a planet, but it could be something else. You want to get at least two of the same characteristic one to show that it's gone one orbit around. If something just moves in front of a star, like in between you and the star, it could be a dip, but if you never see it again, you don't know what it was. It could be something between you and the star. It could be something in our system, very, very close. You don't know. Well, so you would want to get multiple dips that look the same to confirm there are planets. And look, here's multiple planets can transit their star. Now here, well, yeah, maybe you can write down this. Kepler Planet Finder mission. We're talking about Johannes Kepler, who came up with this Kepler's third law of planetary motion, this p squared, the period squared equals a cubed, the distance cubed. This is Max Kepler. On the twins, yeah, I don't know if you know Max Kepler, but I didn't make the slide, but it's a good slide. Yeah, Max, actually Kepler has been asked if because he's from Germany, where Johannes Kepler is from, hundreds of years ago. Maybe he's been asked whether he's related to Johannes, who came up with this law that you can determine from the period, you can determine the distance of the star. But Max said, no, I've been asked this. I know. Yeah, he knew about Johannes Kepler. He said, no, I'm not related. And but here's a spacecraft that it's not really, it's not really working anymore. But for years, we had sent this up. Now, here's the real Johannes Kepler. That's the Kepler it was named after, who figured out there was a relationship between period of the time it takes a star to go around its planet, and also, no, not a star to go around, a planet to go around its star. Actually, they're going around each other pretty much, but the star's not moving much. A planet to go around its star, and also the distance. And this is we sent up a spacecraft early 2000s, and here's what the spacecraft is doing. Here's a term I'd like you to know. The term is called habitable zone. It's also called the Goldilocks zone. I'll tell you why. It is the distance from a star where a planet could be and have just the right temperature where liquid water can exist on the surface of the planet. Because if we want to find life like us, I mean, there could be other types of life based on other compounds, but life like us and plants that are based on carbon, water, we want to search for planets that could have liquid water. And then there's a chance for life, maybe like us, similar to us. I mean, plants, like other maybe life forms that are based on the same kind of things we're based on. Now, take a look at this. This represents the sun, one solar mass, that's the sun. And this represents the blue here represents the habitable zone. The Earth, that represents the Earth there. We're in the habitable zone. How do we know? We have liquid water on our surface. Here is Venus. It is a little too close to be in the habitable zone, so it's not. Mars is right at the boundary of being in the habitable zone. Mars, actually, we think once had liquid water on its surface, and so Mars, it's kind of debatable whether Mars is in the habitable zone or not. Now, it did lose its atmosphere, which kind of affected it as far as keeping liquid water on its surface. It doesn't have much atmosphere, only 1% of the Earth's atmosphere. But Mars maybe once had life. Who knows? Could have life under the water, under the ground, whether we think there's water running under the ground. Well, look at the Earth. We know the Earth's in the habitable zone. What if there's a star that's very massive? Let's say at least, well, not that massive, but 2 times the mass of the sun, 2 solar masses, kind of like a hotter fire. If there's a hotter fire, the star's really not fire, but wouldn't you have to get a little farther away to be comfortable? So the habitable zone for a more massive, hotter star is farther away. What if there's like a red dwarf star, like 0.5 solar masses? Well, wouldn't the habitable zone be closer? If your fire is dying, wouldn't you have to get closer to it to be warm enough? So what the Kepler mission was doing, and again, it's not really operating much anymore. It's a lot of problems, but it did a ton of work. Incredible things it found. It was searching for planets in the habitable zone, in the habitable zones of stars that are kind of similar to the sun, maybe a little more massive than the sun, a little less massive, because if it can find planets in the habitable zone, it's finding planets that maybe could have liquid water, and if it has liquid water, it could have life. It's not saying that if it's in the habitable zone, it's going to have liquid water. We're not saying that, because there could be a very, very low mass planet that couldn't hold in an atmosphere that's in the habitable zone, and it's not going to be able to have liquid water. Water cannot exist if the planet is, the gravity is very low and there's no atmosphere. You're not going to have liquid water. Or there could be a very high mass planet like Jupiter that has no surface in the habitable zone, and it wouldn't have liquid water because it's just a big ball of gas and liquid, no solid surface. So just because you're in the habitable zone doesn't mean you have liquid water. There has to be other conditions, like the planet has to be the right mass to have, it has an atmosphere. But at least if you're in the habitable zone, there's a chance. I'm saying there's a chance of liquid water. And so again, habitable zone, also called the Goldilocks zone. You see why now? Because not too hot, not too cold, just right. The Goldilocks zone. That's a real term right now. Now, let's see what this Kepler mission did. We had it up. It was orbiting around the sun, kind of like kind of lagging behind the Earth in what is called the Lagrangian point. It was searching 3,000 light years, and this represents the sun, our system right here. So take a look, real close up here, looking into a region where I think it was like, we thought there was a high percentage of sun-like stars into this region. It could have looked any direction. And here was the field of view of the Kepler mission, to look for thousands of stars in this region, near Cygnus, actually kind of in the constellation Cygnus, near Lyra, And looking in this region, let me show you another one here. Here is the field of view. Now it shows, oh, look, there look like 10 stars in this area. No, it looked at tens of thousands of stars and analyzed wobbles, not wobble, it analyzed not the wobble of the star, but the transit. So that if the star dimmed down a little bit, remember that we're talking about a transit for the Kepler mission. Kepler mission was looking at stars and seeing if there's a transit of something, seeing if the star dimmed down. So this mission lasted years and years and years. And why did it need to last so long? You want it to have multiple dips in the light curve of a star. If you just had one, it's unconfirmed. But if you had more than one, especially at 2, 3, and then you can have a confirmed object, which would be a planet. Now, this was a couple years ago, and again, it hasn't been much more. The Kepler mission, there's not been much more since then because they kind of had a lot of problems actually a couple years ago. So this was pretty close to being accurate. As of 2018, confirmed planets, 2,600. And candidates that we think that may be unconfirmed because of one dip, over 4,000. Now, it found some eclipsing binary stars where 2 stars were blocking each other out. And so it found some of those. But look, confirmed planets. And as of February, take a look, February of 2017, just a little bit before that, so here's planet candidates, Earth-sized ones. It found 350 the size of the Earth. Super Earth, a little bit bigger than the Earth, over 815. Again, there's data. You're not going to have to remember this data. I don't even remember this data. Just know we found a lot of planets this way by using transits, and especially with this Kepler mission. Neptune-sized ones, a lot of them, Jupiter-sized. Now, look at this. Earth-sized and found in the habitable zones of their stars, 21. And look at the region that we're looking, just in this region, 21. And we're only seeing about 1 out of 50 stars had the alignment just right where the planets would transit their star. A lot of these in here might have planets that we couldn't even tell that there's a transit because it wasn't aligned right. Their orientation of the system, of the plane of the system was off. So, yeah, this is pretty exciting. Just in that region, this tiny region, just looking, and look what we looked into. Just barely anywhere in our galaxy, and we found 21 planets that were like Earth-sized and in the habitable zones of their stars, which means they could all have water. I mean, none of them could, but we think that, hey, a lot of those could have. And if some of them have water, maybe some of them had life. Now look at this. Here's a system, Kepler 22b, and it shows that this one we detect, we think, artist conception may look like this. Again, here's Earth. This would be a super Earth. So a lot of these are, when you see a picture like this of a planet that's not in our system, it's not a real picture. Artist conception. Look at the Kepler 62 system. It had at least 2 here in the habitable zone going around this dwarf star. Now again, if it's a K2, lower mass, lower temperature, where would you have to be in the habitable zone? Closer than our system or farther? Be closer. Be closer. And again, here's Kepler 22b. Here's some data. Now, you don't have to write this down. You don't have to know this. But from the Kepler mission, we think there are over 50 billion planets in the Milky Way galaxy. Now, we're going to be more than that. I mean, at least 50 billion planets in the Milky Way. And they're saying this, based on this data, over 500 million planets in the habitable zones of sun-like stars. Well, if there are over 500 million planets in the habitable zones of sun-like stars, how many of them would be similar to Earth? Well, remember again, if it's in the habitable zone, doesn't mean it's going to have liquid water. What percentage of these 500 million would have liquid water? What percentage? Well, maybe 1 out of 10? Maybe 1 out of 100? So it wouldn't be, let's say it's 1 out of 100. So that means 5 million planets would have liquid water. Now, if it has liquid water, does that mean it's going to have life? What percentage of that would have life? If it has liquid water, I mean, does it have plant life? Does it have, I mean, that would count as life. So of the 5 million planets, what do you think, 1 out of 100 has life? Nobody knows these questions. Nobody knows the answer. I mean, nobody knows the answer to these questions. So it's up to you. I mean, you got to figure it out. But even if life is very, very rare, you have so many planets that could have liquid water that there could be still hundreds of thousands of civilizations, intelligent civilizations in our galaxy, just in our galaxy, and there are billions of other galaxies. Now, still, civilizations might be so far apart, we may never contact one, or one might not contact us. And a lot of civilizations maybe just have plants. I mean, plants and other, maybe animals that can't communicate with us. So, I mean, imagine, dolphins are incredibly smart, maybe smarter than humans, but they don't have the technology. They don't have, like, opposable thumbs. If they did, if dolphins had opposable thumbs, they would be doing what we're doing, probably better. I mean, the Miami Dolphins would actually be dolphins and not people, and they'd be winning the Super Bowl all year, or not all year, but each year. So, yeah, we could have intelligent animals out there, intelligent creatures, but maybe not the ability to communicate. So there's also the idea that civilizations, a lot of civilizations gain intelligence and the ability to communicate out there, use radio waves, but they don't last that long because their ability to handle their technology outweighs their their lack of ability to handle the technology outweighs their technology, which means that they destroy themselves. Now, does that kind of sound like us right now? Kind of what's going on? I mean, not just in the last few months, but things have not been good for us. I mean, polluting our whole planet. I mean, overpopulation. I mean, that's a big problem. A lot of issues where we're kind of, destroying rainforests, destroying animals, destroying each other. So there are ideas out there that civilizations may, make it up to technology, but they cannot handle it very well, and they don't last very long. I mean, if it only lasts for our civilization, a technologically advanced civilization only lasts for a couple hundred years, maybe another 100 years from now, and we're done. I don't like to think about that, but we got to change what's going on now in order to not have that happen. That means there may not be very many civilizations out there for us to talk to. But if people learn, or we learn, other civilizations may learn. There could be millions more civilizations out there. So it all depends. There are a lot of factors. Nobody knows. So what else here? Now look at this. Kepler 16b. And again, named after Kepler, these systems, because the Kepler Space Telescope found it. Here's a Saturn-mass planet right over here. And it's not going around one star. It's going around two stars. So if there were, let's say, this is Saturn-mass planet, which means there's no solid surface. What if there's a lower-mass planet here that we're not detecting yet? There's a good chance. That means there might be two stars in their sky. Two stars in their sky, which means that, remember a movie that had, you might have two stars, a star set of two stars. Well, look at this. Remember Tatooine? Remember Luke? You got to remember Luke. I guess you probably should remember Tatooine. Remember the scene where in the original Star Wars, A New Hope, and do you remember this where he sees the two star set? Well, come on, science fiction people thought, Star Wars. Well, no, not science fiction anymore. There are probably planets out there that have a double star set. Not Tatooine. Tatooine is not here. Remember, Tatooine is in a galaxy far, far away. So it's not here. But we could have we don't need Tatooine to have this. So it's not science fiction anymore. We have things like this going on. Now, this is another representation of multiple stars in the sky. Now, here's you don't have to write this down. TRAPPIST means the Transiting Planets and Planetesimal Small Telescope. Again, the astronomers try to get acronyms for words. Actually, they come up with an acronym, and then they make a sense after it. They do some weird stuff. You should know that by now. Well, look what it has discovered. Now, there is a M8 spectral type red dwarf, low mass, about as low mass as you can get for a star. Remember, M9 would be the coolest star. Here's the size of the sun. Here's the size of the star relative to the sun. So very, very small. They're very small, low mass, low luminosity. But look what we discovered based on transits around this in this star. Now this is our system, the solar system. The sun here, and here's Mercury, Venus, Earth, and Mars. Now look, if you zoom in to there, and imagine that all of this would be going around its star. There's that low mass star. This is the habitable zone, very, very close to the star. And look at this. We have found what is something like seven planets in the habitable zone of the star. But look, the star is to be in the habitable zone of a red dwarf star, you got to be close to get warm enough to have liquid water. Look how long it's taken. Now, these are, again, artist conception. This planet takes 1.51 days to go around its star. 1.51 days? We take 365 days, 2.42 days, 4 days, 6 days, 9 days, 12 days, about 20 days. And this is the planet's radius, in the radius of the Earth. They're about Earth size. This is about the same size as Earth. 1.09 times the diameter radius of Earth. 1.006, 0.77. These are all about the size of the Earth. They're really tucked in close to their star, but they're in the habitable zone. They're in the habitable zone. They could have liquid water, but the problem is this. If they're that close to their star, they're going to be tidally locked in. One side of the planet is going to be always facing the star, and one side's facing away. So one side's going to be really, really warm, and one side's going to be really cold all the time for each of these, which means if you're going to have liquid water, well, it's going to be probably water vapor on this side. It's going to be ice on this side. You'd have to be right at the boundary, the terminator, the day-night line, maybe to have liquid water. If there's any civilizations here, any life, that like it like a pleasant temperature, like we like it, well, what we call pleasant, 70, 60, 70, 80 degrees, they're going to have to live over here, right at the terminator. And they're always going to have their star right at the horizon. It won't ever be high in the sky. So this is a weird place. This would be interesting to visit this place. And, yep, that's it. There it is. There's extrasolar planets. Stay tuned, because we're going to start talking about evolution of stars. So, but planets, got to talk about the planets. Exciting out there. Planets going around the stars, maybe one of the most exciting topics in astronomy. So, until next time.